Okay. Yeah, we are glad to have Ratul Bhaiya again. So, yeah, over to you,
Thank
Ratul.
you. So uh, okay, so last day we discussed a discretized version of a two-dimensional Lorentz scalar field theory. And just to motivate and to see what is the scheme in quantum field theory, basically the Hamiltonian decouples in terms of harmonic oscillators. There are a collection of harmonic oscillators that describes the quantized system. And then we started discussing the classical theory of fields. We saw the Euler-Lagrange equation, and we should now discuss the symmetry. So I also mentioned what symmetry is. So it is change of phi, so trying different functions for phi, such that the action remains invariant. Okay, so we saw what is a okay, somebody wrote that. Is it visible, like my screen? Is it shared? I think yes.
Yes, yes, it is visible.
Okay. Uh, so we saw a discrete symmetry that was phi going to minus of phi, and wrote an action which has this symmetry. Today we'll mention what is continuous symmetry. So by an example, so I will be considering an action which is this. Okay, so from now on, we will be only focusing on fourth dimension, fourth space-time dimension. And it's the Minkowski metric is 4x4 matrix with mostly minus signatures. Okay, so consider these. I think there is a factor of half. I mean, it depends on convention, but let me put it here. Okay, so what is phi? Phi is a complex field. So it is basically two real fields and a complex combination. So the action is so written so that it is real. Therefore, the complex field and its conjugate is also used. This we will be dealing with in a exercise, like Rakin has prepared a nice exercise, and it can also be found in books. I will not discuss this type of theories, but I mean in detail, but you can see that if you change these at each point x, if you change these by this transformation, so here alpha is a continuous parameter, therefore phi star changes as this, and alpha is independent of x, the space-time. So you can see that even from the derivatives, this e to the power I alpha and e to the power minus I alpha will come out and they will cancel. So therefore, under this change, and this is for any arbitrary field for which you could compute the action. So phi, the action for the phi and action for the phi prime, I should say that this is phi prime, x equals to this. So it is same. So these type of symmetries are known as continuous symmetry. On top of this, since alpha is not a function of x, it's independent of x, so it is known as global symmetry as well. Continuous plus global. Okay. So we will be dealing with local symmetry as well, where you will be allowing alpha to be dependent on x, but in that case you need to modify the action, the Lagrangian, and those will be called like they will be dealt in gauge symmetries, and Taushik will be teaching them. So for time being, we will be only focusing on the continuous global symmetries. Okay, so discrete and continuous symmetry. Continuous are of two type, like two type, the global and local. Now I will be talking about space-time transformation. So many often the symmetries are given in terms of space-time transformations. So space, which probably you can call space-time symmetry. I'm not sure about terminology. You can maybe find it in books. Okay, so what are they? So you will change the space-time, which will be given by some x prime as a function of old position. And you will also see how the fields transform. So field will transforms like some functions of the old fields. So these two together will constitute a symmetry. Why? Because action is not sensitive to x or x prime, because x is integrated out. So what is action really sensitive is what is this delta phi x at each location, which can be defined by this. So, okay, so this we will understand through some example that given the set of transformation as mentioned here, how to get the change in field at each x. So, for example, consider translations. So it is a continuous shift in the space-time. There are 4 parameters, a mu, and they are arbitrary, continuous parameter. We are not, yeah, they are set of parameters which you can take as continuous parameters. And the fields are the oil. I have only considered here one type of field. So it is a scalar under translation. So that's what we will require. So basically, given a Lagrangian, we also need to specify what are the transformation properties, and we will specify the transformation properties this way, so that you have to tell. So we will always specify this transformation property like under translations. So translations, all under translations, all our fields will be scalar. Okay, so from here you can actually see that what is delta phi x? You can compute from here. This is nothing but this. So that's how you need to change the field at each x. So although we started from changing both x prime and x to x prime and field to phi prime x prime, but you can eventually compute it at each position, and this is the one you should plug in the action. Okay, so next thing we will be considering uh, uh, okay, so we should start with an action and show, see that whether it is a symmetry or not, but that we will be doing later. First, let us see mode space-time transformations. So another possibilities are Lorentz transformations. So this is where you change the give the Lorentz rotations. Rotations, quote unquote, like if you change the positions by Lorentz transformation. So basically, this set of four components of the four vectors mixes under these type of transformations. That is the Lorentz transformations. And phi prime, I am thinking it as a matrix now. So already here we are dealing with multi-component. Like now the fields phi has say set of components, so that a matrix representation of the Lorentz group can act on the set of components, and it can mix. So that's the most general case. For the Lorentz scalar, these things should be identity. Then we will be calling all the components as scalar, or you can just consider a single component field. You don't need to consider a multi-component field. Okay, so what are Lorentz transformations? They are the ones which keeps as a matrix, they leaves the eta invariant. So lambda transpose eta lambda equals to eta. And in the continuous symmetry, although here A was a finite parameter, but in this approximation, in the second line, I have taken the infinitesimal transformations, space-time transformations, and that's why, that's the advantage of having continuous transformation. You can continually change, and you can take the parameters to be infinitesimally small. So we'll now consider similar situation here. So for infinitesimal Lorentz transformations, these eta mu nu is nothing but something connected to identity. So basically, you will be changing slightly from the identity matrix by some set of parameters omega mu nu. So if you plug this, you will see that at linear order, this cannot be, it has this set of parameter has some property. So let me do it here. So this relation tells that eta mu nu lambda mu rho lambda nu sigma equals to eta rho sigma. And From there, you can see that essentially it will lead to something. I have to check what are the indices, but this is anti-symmetric. You can derive this property. So this set of parameters which describe the infinitesimal Lorentz transformations are anti-symmetric. So it means you can now count how many independent parameters a 4x4 anti-symmetric matrix can have. So the number is 6, and 3 of them are the Lorentz boost, and 3 of them are the ordinary three-dimensional rotations among the on the spatial dimensions. Okay, so L lambda will also consider some infinitesimal version of it, and this is, and whenever this is a matrix, because L is a matrix, so S should be a matrix, but this is an antisymmetric antisymmetric in mu nu index. Why so? Because it is multiplied by omega mu nu, and omega is an antisymmetric parameter in the mu nu index. Therefore, only the if you allow any symmetric part in the S, that will not survive. So it's better by definition take it as antisymmetric under mu nu. Okay. So you can see that this is basically an infinitesimal version of this. This is the infinitesimal version I have written, but let us talk about the infinitesimal version. So usually that's how we will be treating any representation of a group. They will be exponentials. Okay.
Do you want to take a few questions? Quick
Yes,
questions?
I can take it.
Okay. One of the questions is the alpha equation real? Is alpha in the equation real? Sorry.
Where is I have written probably A. Is
No,
this
on the very first page when you are writing the U1 transformation.
yeah, alpha is real. Sorry, I should yeah, that's a
Okay.
real parameter. Yeah.
So next question is, can the translation be considered as a gauge transformation?
Translation. Well, the parameters are mu. They are independent of x. So for gauge transformations, the parameter should be local. If you define gauge transformations that way, then it's not a gauge transformation.
Yeah, may I comment on this? Actually,
Yeah,
no,
please.
this translation actually is not Lorentz transformation, sorry, gauge transformation. So that I will introduce in my lecture. Okay, so this is not, this cannot be considered as gauge transformation.
Yeah, thank you. Yeah,
We'll
so
deal
the
with
gauge
gauge
theory will
theory.
be dealt by Taushik. So it's on him, and please ask
Also later
questions
on,
to
there
him.
will
Yeah.
be some other.
Yeah, I
some-
think he will initiate, and then Nabil and mostly Gonzalo will also talk about gauge theory. So yeah. So okay, what is the next question? Maybe one more questions, and then we should continue.
Yeah. I think two of them had problems following. They asked a bit slow to slow down a bit.
Like the writing speed?
Probably.
Okay, it's not probably possible because I have to finish like many things in 4 lectures. So I will be uploading my lecture notes. So I have already, I mean, Rakin has uploaded my first lecture, although I have 3 lecture notes, which I will be delivering in 4 lectures. So you can find all the details there. So it's okay if you do not write down anything, you just try to follow what I am saying. It will be okay. I think
Uh,
so.
okay, and
Okay.
there's
Yeah.
one question about some, I think there phi being primed in some equation. Uh,
Maybe
okay,
20 minutes later, I will take
yeah, okay,
a set of questions and people can directly ask me.
okay.
So now the infinitesimal transformations for, okay, so we have to compute what is delta phi for the Lorentz transformations, and that we will be computing now, and it's by the relation I mentioned, the property, transformation property I have given. From there you can compute. So this is x mu plus, and this can be on the other side, it is uh, uh, L of lambda acting on phi. So this you can write as, because it is identity minus something, so you can write as x minus the S mu nu acting on phi x. So you can see that since this is multi-component, S has to be a matrix that can act on it, and immediately you can compute by taking a Taylor expansion on the left hand side. I am not going in the process, but in the lecture note you'll be these details are there. So this will be okay. So this is the transformation property. So you can see one thing here. Okay, first of all, whenever something is multiplied by omega, I will only consider the antisymmetric part. That's what I have written here. Because, and that's why this factor of half also came for the first term. The second term has, by definition, I had taken a factor of half because in an antisymmetric matrix, only 6 of them are independent. Therefore, to avoid double counting, I had already taken a factor of half out. So this is what, but one thing is you can see that what point is invariant under Lorentz transformation, that is the origin, because this any matrix acting on the origin leaves it invariant. Therefore, at origin, what is the delta phi? This is nothing but yes. So you can see here that at origin, the fields mix among themselves. So this multi-component are mixed by a matrix, which is a representation of the Lorentz group that mixes the generators of the Lorentz group that mixes this multi-component. So this is an intrinsic spin even at the origin, which is not affected by the Lorentz transformations. The field can rotate, or I should say that mix among themselves, and so that's why well, for scalar this S mu nu is basically 0, because if lambda L of lambda to be identity in the exponential of something, it should be exponential of 0. So S mu nu is 0 for scalars, for Lorentz scalar. So for them, there will be no rotations among the components, or you can consider only single component. So this is the thing. Now the question you have to ask, given these transformations, that given an action, we need to plug these transformations delta phi and see that whether it is a symmetry or not, and then we will be calling it a continuous symmetry of the action. So let us assume that the action has symmetry, because whatever I will discuss now, I will not discuss in any specific Lagrangian. I will now discuss a general theorem called Noether's theorem. It's about the it's about some concept quantities associated to a symmetry. So let me first state the Noether's theorem and then try to prove it. So okay, for every continuous global, this is important, symmetry of an action, there exists a conserved current for classical field configuration. That is also important. So we will be discussing, try to prove this. And eventually it will also be clear what it means. I will assume that so there are two ways. So given a transformation, you first compute what is delta phi x and plug in the action, or you can manipulate the action since x is a dummy variable. That's what I will do here now. So s of phi prime, let us start computing this. Suppose there is a transformation, a continuous transformation that takes phi to some phi prime x, and let us start computing this, and this is and since x is a dummy index, you can just label it this. And we have seen that most of the transformations are given in terms of phi prime x prime. So now we can directly use them. So that was the advantage of this variable transformation x to x prime. And it's the integration variable that you are transforming. Now this is nothing but the Jacobian of the transformations. And okay, I should also, I will be telling you the transformations in more detail, but like the infinitesimal ones, so that the notations are clear. And this should be by chain rule. Okay, so the transformations are infinitesimals. It was given by computed as a function of x. So what are these variations? These you can actually, any transformations given these, you can compute what was the extra piece. For example, for translation, it was mu. So I think, and the set of parameters had a Lorentz index. So here I is not necessarily a Lorentz index. However, Yeah. So this you can, from here you can compute what is your x mu. Yes, del x prime mu del epsilon I. Let me just proceed, see that whether I will be discussing it later. Yeah, so I will be discussing it later, so I'm not discussing it here now. Okay, so let us stick to the general transformation. So that's how you will have, and also you will change the fields. So this is again the old field and the set of parameters times something. This you can always find given a transformation, what are they. So you can also compute. So what are the quantities we need to compute? We need to compute the Jacobian. We need to also compute these quantities, and you can use them. So for the Jacobian matrix, so x prime mu del x nu is nothing but delta mu nu plus del mu of epsilon. Yeah. So we will be dealing with continuous global symmetry. So eventually we are going to allow epsilon to be independent of x, but suppose I want to arrive at the Noether's theorem, but so far we are considering in general transformation. So you can allow epsilon to be x dependent for the derivation, and eventually we will say that x is independent. These epsilons are independent of x, but I am keeping it inside the derivatives. Otherwise you can bring it out, but it doesn't matter, you can anytime bring it out, but think them as we do not know, we just given a transformation. So these are the ones, and epsilon can or cannot depend. We are just computing s of phi prime, and we don't know whether it is equal to s of phi or not. So okay, so and you can also find the inverse, which is this, and the inverse at linear order is nothing but one way is you multiply these two and check that at linear order this gives an identity. Otherwise, other way you can yeah, so that's one easy way, but other you can some details are given in the notes, and one can compute the Jacobian. Jacobian is the determinant of this matrix, and we know that determinant of identity plus x is 1 plus trace of x whenever x is very small, and which is true for us because this quantity has this infinitesimally small parameters epsilon I. So the determinant of this will be 1 plus the trace, and for trace means the trace of this matrix means setting mu equals to nu and sum over mu. So that's what we have done here, and it's following the Einstein summation convention. And you can also find this. at linear order, you can see anything which is square in epsilon, I am dropping. Because epsilon square is smaller than epsilon for our case. Okay, so these are the properties, and we wanted to compute S of phi, and you can phi prime, and this is nothing but now 1 plus So this is the arguments in the Lagrangian. It has two arguments as usual. So you can now see that if you take the linear, what is the zeroth term here, like the leading term? So that is nothing but S phi. It will come from these and these arguments. So this will lead to the S phi, and then you can collect terms which are now you expand like every quantity. For example, wherever there is a derivative on epsilon I, you consider it as a function of x, because we are not demanding that it is a symmetry, and we are just trying some set of transformations, although infinitesimal, given like here we are trying these transformations yeah, we are trying these transformations, and we don't know whether they are symmetry or not. Allow them to be x dependent, and therefore there are two terms where there will be derivatives of epsilon, and since epsilon is multiplied by some other quantities, for example, this kind of quantities, therefore there will be something epsilon times derivatives on the other quantities. So these are the terms you will get, and you can collect things which are proportional to epsilon. Of course, it should have an index I, because it's eventually should be summed over, and there will be some quantities which will be I am, whatever is there, I am defining at minus j mu I. It's a definition which will be this. So if you expand, take the tailored expansion of the previous line, and you will find these kind of terms. And I am particularly, you can keep track of what are proportional to del mu epsilon, and you can find what is j mu I. It's easy from here also, but I am just writing the what it is. So this will be okay. That's great. So now demand that it has a symmetry under only global transformations. But anything, I mean, action is meant to compute for given any phi, right? So you plug phi, you get the action. Demand that it has a symmetry under global transformations only. So you know that whatever terms appears, if it has to be a symmetry, these two quantities should be equal. S phi prime equals to S phi. And since for global transformations, this term will not be there, the del mu of epsilon. So only terms that should be there are these terms, but since it has a symmetry, whatever appears there should be 0 identically. So that's what symmetry mean, and you can actually check given Lagrangian that this is happening. It's you can take it as exercise. Wherever you find a symmetry, you check that the linear terms go away, and that's what symmetry means. But suppose for those actions which have a symmetry under these global transformations, if you allow this to be x and compute the s of phi prime, you will get this, because it has a symmetry under global transformations. The proportional to epsilon terms or identically go away, but this leaves. And you can and it's not a symmetry. You can see that I did not demand that it is a symmetry, but thing is that when suppose we are considering phi equals to phi classical. What does phi classical means? Phi classical means that any variations under these classical fields, action has an extremum. It means that delta S vanishes. So for those fields, earlier symmetry was for arbitrary field phi. We don't need to solve for classical equation of motion. Now I am considering very particular field configurations, which are the classical ones, and variations under around classical field should be 0. For those, you can see that this should this quantity, these two should be equal. Therefore, the second term should be equals to 0. So whenever action has a global symmetry, this vanishes, but when you compute around phi classical x. So this implies and you can allow any arbitrary variations. That's what extremization problem mean, that it's really a classical field if you allow arbitrary variations, and variations are here through some epsilon x, and this is arbitrary, which immediately imply a conserved current. So this is, of course, I should mention that this is around the classical field. Okay. So I am again stating the Noether's theorem that for every continuous global symmetry of an action, there exists a conserved current for classical field configuration, and immediately you will get conserved charges. So conserved charges are Qi, which are okay. So I had a set of currents for each I. Like for I have currents for each I, J mu, and the 0th component, if you integrate it over the space, then it should actually depend on time, but you can compute that this is this Q is time independent, and that you can show by this, and then taking an using the property of the conserved current. So this tells you that J0 is minus del A JA. A runs over 1, 2, 3, the special indices. So that's what a conserved current mean, and you can write it as a divergence. Oh, I should write A. Sum over A is there, so it is a divergent, and it's a boundary term, and at boundary it is 0. We are assuming that the fields, last time we considered that everything is computed around phi classical, okay? Yeah. So last time we assumed that the variations of the fields dying away, but now we are also at least recording that, because if you integrate this out, you will get the boundary terms, and setting it to 0 means we are setting the fields go away whenever Tx goes to the boundary. So that's something we are assuming here, that we will be assuming. So you can see that the charges Qi are independent of time. So they are the, so the integral, special integral of the zeroth component will be conserved quantity along the equation of motion. So that's where I should take a break, and I will I'd be happy to answer your questions. Yeah.
Yeah, there are some questions there.
Yes, please. You can allow them like for if they raise
Okay,
hand.
yeah,
Yeah, yeah. Because then we'll have a break after the
okay, yeah,
questions,
sure.
and yeah.
Okay. Okay, very a lot of questions.
Yeah, just whoever raises hand, you can maybe
How
allow them. I don't know.
okay, continuous global and local symmetries. Someone asked about it. Like a little bit, like can you talk a little bit about continuous global and local symmetries? That is the question, basically.
I will not be talking about local symmetry. That's Toshiko will be initiating. So just not to confuse, maybe we'll be talking about, whenever I am talking about symmetry, it will be global symmetry. They are not dependent on X. And whenever they are not dependent, they are X dependent, then it is not a symmetry. You can see that there is an extra term. But this extra term go away only when you are considering variations around the classical fields. Okay.
Okay.
Yeah, please allow them to.
Yeah. Let me ask a few from the chat, and then I'll allow one or two questions.
Yeah.
Noether theorem, local symmetry and global symmetry too. It's and question mark.
Well, as I
I mean,
stated that it's only for global symmetry, and I think I have outlined the proof, and you can see that I have only assumed global symmetry. And then the conserved currents are along the classical configuration only. So that was a key point in my derivation, that it's only for, we assume the symmetry is for global transformations. The parameters epsilons do not depend on X. Yeah.
okay, two more from the chat, and then we'll allow some people to
Yeah.
speak.
Yes.
Can you clarify epsilon?
Oh,
What is?
so that's what I wanted to do next. But it's good that I should start Klein-Gordon field theory after the break. So let me have the opportunity to say what is this. For example, say under translations, you can immediately see these are the epsilons. Earlier I called epsilon I, but this epsilons has mu index. Therefore, whenever you compute this quantity, it will be nothing but delta mu nu. You can see that you can arrange this thing as x mu plus a nu is the I index and something this quantity. So for translation, that's what is the parameters. And take an exercise that the conserved quantity, earlier we had the current had an mu index and an I index. Now we'll have mu and rho index. That will be called energy momentum tensor. And following the formula I have given for J, you can see that, okay, so this is epsilon. You can see that this becomes what? This becomes delta nu, and of course there is a mu index coming from epsilon. If you are careful about that, I am considering under translation everything is scalar. So f is 0 because delta f is 0. Here you can see that for us, if it is scalar, only the first term survives, the second term will go away. So from there you can see that the energy momentum tensor is this quantity multiplied by delta, and which you can finally bring to so this is the energy momentum tensor. And what are the zero component? Zero component are the conserved momenta, like the integration of them. Especially you can see that P0 is H. You can read off that when I should call it P for P0, the zeroth component, it is nothing but yes, so sorry. Yeah, for zeroth component, it would be integration Tx T0 0, and this is nothing but D3x and del 0 phi, and yes, this is also del 0 phi. So this is, I should say, phi dot minus L. This is the Hamiltonian density. You can, so if you consider if your action has translation symmetry, which we will have, H is always conserved quantity, and so has spatial momenta. So yeah, so that was the answer. Like, it's a long answer, but yeah.
I think the question was actually about the parameter epsilon. What is it doing?
Here it is a mu. It's the continuous parameters. Like it is shifting here. After the break, I will start discussing the okay.
Yeah.
Let me actually tell about the Lorentz one also, and then I stop. So for Lorentz transformation, it is what? So you know that x mu goes to x prime mu plus some omega mu nu x nu. So these are the parameters. So under which they had the symmetry. And suppose you consider that you are dealing with a Lorentz scalar. Lorentz scalar means phi prime x prime is some identity times phi x. So it is identity. So it's nothing but phi x. So suppose you are dealing with Lorentz scalar. So for that we will have delta f delta omega mu nu equals to 0. And you can compute the conserved current, and you can see that how many parameters are there? 6. You can actually compute the charges. So it will have of course the j, which I will be calling here m, will have a mu index. It is the j mu, and I is here what? Some Lorentz indices. So it is rho and sigma, and you should be able to show that it is nothing but t mu rho x sigma minus t mu sigma x rho, and the conserved current is rho sigma, especially if you identify it jk for I equals to 1, 2, and 3, the spatial directions, they give you angular momentum. So it has both boost and angular momentum, but the ij components, if you arrange it in a special way, you can identify the angular momentum. The exercise should be derive these things for theory of Lorentz scalar, and check explicitly that this vanishes. For this, you need to use the Euler-Lagrange equation, because it is true only for classical fields obeying the classical equation of motion. So that's an important thing. So yes, I can now start the quantizations or the Klein-Gordon equation, but I will take questions for 5 more minutes and then break for 10 minutes. Yeah. So I think now it is clear that what are these parameters. So this is some parameters. For example, for the transformation I talked about e to the power I alpha phi. So this is the epsilon. It has no index. For translation or Lorentz transformation, it has indices which are some I, but which also are Lorentz indices. So that's what you will be saying. Yes.
Yeah, I think that answers. I think we can open the, if anyone wants to ask directly, you can
Yeah.
raise your hand and we can unmute you.
Will you record this session or?
Yeah, recording has already started.
Okay.
So I don't see any hands up. Oh, there's one more question in the chat that I missed. Why both x and phi transform using the same parameter?
Well, that's will be that's the given thing. Like for example, like whenever you write a field theory, you have to state that what are your fields. Like are they scalar? Are they spinor? Are they, what are they? Whether they mix under transformations or not. So usually we will be demanding that if you take the translations or Lorentz transformations on the spatial for x mu, like the space time, if you change space time, then how to change the field so that your Lagrangian, or I should say that action is has a symmetry. So we will be considering Lorentz invariant actions. It means that you have to assign your transformation property to actually it would be sufficient to just state this, because action is only sensitive at each x, and it has some parameters epsilon I. But in our symmetries, they are also coming from some space-time transformations, because that is what we will be demanding, that our action has those symmetries. So we want a Lorentz invariant theory, and those will be the like relativistic theory. So, but anybody could come up and directly one can directly give me these without stating that they are coming from space-time or not, and there will be some parameters, and that's what action is sensitive to. Yeah.
Okay, I think we can go for a break.
Okay, so we have discussed about symmetries, and we saw that it leads to conserved current, and I have given you the exercise to check that these conserved currents are there for Lorentz invariant and also translation invariant theories. And to check them explicitly, you need to use the Euler-Lagrange equation, because only for those field configurations they are symmetry. Now I will be dealing with Klein-Gordon equations, and that's okay. So the idea is I will discuss Klein-Gordon field, which is a Lorentz scalar field, and then I will also discuss a spin-half field, which is the Dirac field. So in the next 2 lectures also, I will be mostly dealing this. Okay, so I think yeah. Okay, so first talk about the Klein-Gordon equation. Okay, so you know that for non-relativistic free particles, the energy momentum relation is this. And for getting the Schrodinger equations, I mean, we wanted to interpret it as some quantum system. So there will be a wave function, and what we did these substitutions. Note that since I am writing del x I is lower, and so pi is lower, I am not introducing the minus sign here. But you can define it as p upper I with a minus sign. That's in the just to well, in when that's coming from relativity. But what is more familiar to you may be this. But when we will be doing relativity, we should take this when we are talking about lower indices. Like, okay, so this will lead to a Schrodinger equation. H cut is again 1. And you know that this admits a plane wave solution, which is it is you can try this solution, and it is a solution only when E square equals to this. Yes, like sorry, E square equals to P square by 2m. So for relativistic particle, it is not E squared, it's E equals to P square by 2m. Okay, so for relativistic particle, the energy momentum relation is this. And if you just make above substitutions, because you want to describe the quantum mechanics, say, for the free relativistic particle, the first take is you substitute these quantities, epsilon E goes to I del del T, and Pi goes to I del del Xi. But you cannot progress because it would be a square root of a differential operator. So there are many roots. One root, there are two roots. One root would be you square the equation. And these will lead to an equation you can also combine it. This will be this, I think. Okay, let me check about the sign. Okay, so this is plus. Yeah. So it can be written in a compact notations. So this is what known as Klein-Gordon equations. So of course, the original motivation was to write a Schrodinger-like equation and interpret it phi as a wave function, but it has some problems. I will briefly discuss because I just wanted to mention about what is the Klein-Gordon equation is. Yeah, so yeah, I think about the sign I am right. So you can check it if this is correct. Yeah. So okay, so the problem is it admits a plane wave solution, but with energy as this, it means it can allow both positive and negative energy. And that's a problem because like if you interpret it as a wave equation and it is phi is your wave function, and therefore you have two eigenvalues, and since P is arbitrary, well, negative eigenenergy you have seen in a square wave potential as well for the bound states, but since P is arbitrarily large, the spatial momenta, therefore, this energy can be negative unbounded from below, and which we do not want. So these are the issues with interpreting it as a wave function, and we'll avoid doing that. So we'll also not discuss much then. So we'll use these equations. So that is the Klein-Gordon equations. But in a different way. So for us, phi will be for giving a consistent interpretation. So for us, phi will be fields. So we want a Lagrangian such that the Euler-Lagrange equation is Klein-Gordon equations. And why so? For example, first of all, for our case, phi's are not wave functions because phi's are our degrees of freedom. Actually, in a quantum field theory, a wave function should look like a functional of this, right? Because if you know that in quantum mechanics, the wave functions are functions of x and t. X are the degrees of freedom. For the degrees of freedom is phi itself, and there could be some discrete level as well, and this. So wave function, if you really want to write a wave function for a quantum field theory, which we will not be discussing in this course, you have to take a functional of your degrees of freedom. So that is what, but we will not be discussing that. So our we'll be now dealing with Klein-Gordon field. The idea is the Euler-Lagrange equation is same as the Klein-Gordon equation. Now you will say that why we require that. Anyway, we are trying to get some equation from this energy momentum relation, and we wanted to interpret it. We'll see that in the field theory interpretation, we will not encounter any negative energy states, and we will be discussing what the particle states are, which will be some creation and creation operator acting on vacuum, and that we will be discussing, but phi will be fields, not wave functions. Okay, so now I should discuss about the Klein-Gordon field. So it is KG field. And we'll develop and we'll interpret that whether they are really giving the free particle states or not in these classical, if you quantize the classical field theory. So this is real and it would be Lorentz scalar. That is the case we will be dealing. You can also deal complex scalar. That is probably an assignment. And the Lagrangian which we will be taking is the most discussed Lagrangian so far. And in Hamiltonian dynamics, you actually treat time and position differently. So I am writing the position derivative and the spatial derivative separately. However, in path integral, you can use, you can have a manifest Lorentz invariance. So the Euler-Lagrange equation of motion is will lead to what you have just seen. Okay, so this box is a fancy notation for this operator, the Laplacian operator. So this is the Klein-Gordon equation. So we have got the Klein-Gordon equation as a Euler-Lagrange equation, and the usual prescription that I have given last day. So you can compute the, and this prescription will be same. Like once you have a Lagrangian, you compute the conjugate momenta, you write down the Hamiltonian, you impose the Dirac prescription for the equal time commutator, and you get the quantum dynamics. So that's what will be same for that was same for the discretized version, that will be same for this KG field, and that will be same for Dirac field, and also for Taussig as well. So you can see that this is nothing but this is the conjugate momenta. Hamiltonian density will be phi dot x minus the Lagrangian, which is eventually, you can fill these details by yourself. And I am writing Hamiltonian as function of t. It is because only the position is integrated out, but it is independent of time. Why? Because we just discussed that it has a translational symmetry that you can check, and for translation, even the Dirac field or every field, we will always assume that the property is this. So under translation, all our fields are scalar, and you can check that it is a conserved current. It's a conserved charge. So Hamiltonian is the time invariant, and I am not doing that procedure here, but we'll eventually see in terms of creation and annihilation operators, it has no time dependence, and that is another confirmations. But let us try to solve it. So the trial solution would be this. I am taking many fancy factors out. It is because the A and A dagger, small a dagger relation will be later nice. But the in the books, you can find the systematic procedure. So K is K0 and K, but K0 has some omega dependence, call it omega K. We don't, sorry, it has some K vector dependence, call it some omega K. At this stage, we don't know what it is. We don't know what is omega K. We'll plug this and check, find what is omega K, and that we can do. But before this, I want to state that our phi was real. So the reality condition immediately state you that A star K is BK. That you can find out. And the integrals are here actually a triple integral. All are minus infinity to plus infinity. Now try that it is a solution. I mean, take this shortcut approach. So these operator will, they are the position dependent operators, like they act on derivatives of the position. So they directly will act here, the exponentials, because the only position dependent parts are those exponentials. Therefore, you can see that by the way, it will be soon clear that why I have written 2 pi cube. I'll mean and a square root. Usually, like in the Fourier transform of delta, there is a 2 pi cube hanging, and like in the position and the transformed like momentum space, we are having 2 pi square root of 2 pi distributed there. But anyway, so if it acts on this exponential and the box acting on plus minus k dot x is nothing but ik square e to the power plus minus ik dot x. It's nothing but minus k square plus minus ikx. Okay. So this you will get.
There's a question if you want to answer.
Yeah, please ask.
So can you please repeat the steps you just described some time ago? One, you have a Lagrangian, then you compute the conjugate momenta. After that, I lost you. That's the
Okay, so it's I should mention because it would be same for the Dirac and also for Taussig. So given a Lagrangian, you get the Euler-Lagrange equations. You get the Hamiltonian by through the conjugate momentum, and then you try to solve the Euler-Lagrange equation. Basically, the Fourier modes, you promote them as operators, and then use the equal time commutation relations for the conjugate canonical conjugate variables, like the Dirac prescription to some IH cut delta. So that's how we will be quantizing. It's same as what we discussed last day. Okay. So you can see that it is 0 when this minus k square plus m square is 0. It implies immediately omega k is, we are taking the positive one. Because last day I have discussed that if you take the negative one, you can proceed, and it is instructive that you do at home. And you find that what we will be calling creation and annihilation operator, they will be just interchanged. So it's just a convention. Otherwise, I need to define A star k as some bk, and ak will be b star k then. Okay, so this is a just I want to, yeah, so I have actually discussed this in my lecture notes. It will be uploaded, so please read from there. I will not explain that procedure, like what would happen if you have the omega k negative. Okay. So at end we will see that this omega k will appear in the Hamiltonian, and we will have the positive energy states. Okay, next we will be treating them as operators, the mode. Okay, so we have treated A and A star as A and A dagger. They are operators, and you can compute what is the conjugate momentum, and you will find it nothing but this. Okay, by the way, when I write this, I am already know what is K0. It is given by this dispersion relation. So from now on, whenever omega k appears, because we earlier we tried some solution, and we only when omega k is this dispersion relation, then it is a solution. We will be taking this only. So you can see that here the quantities only depends. So K0 is not free. K0 depends on omega K to finally the K vector, and therefore, okay, let me write it. So I omega K T. So I K dot X is I omega K T plus I K dot X, and this is now you can integrate out the k vector, which is the which is the k1 spatial momenta from minus infinity to plus infinity, and you will have a function of time and position. Okay, so the pi x is given by this. And you can I have stated what is the Hamiltonian for this system. It's there, it's the Hamiltonian density, and you should integrate it out. So what is the idea? You see that in the Hamiltonian density, what appears? Pi x appears and phi appears, and their derivatives. So it's a some work is needed to show the following result, but I'm just sketching it here. That if you plug pi and phi in terms of the operators A and A dagger, so in the Hamiltonian, there is a position integral, and then there is then the quantities that appears here, you are writing them as some k integrals, and you do the position integral first by switching the variable. The limits of the integrals are independent, so you can actually switch this, and finally what you will get, you will get and you can see that these are the time independent constant, right? All the time and position dependence are from the exponentials. A and A dagger are time independent, and this is really time independent. And it was basically in the trial solution, it was the constant of integrations. Okay. So I will, this should be an exercise, and another exercise will be finding the commutation relations between AK and AK dagger from the commutation relations between pi and pi. I will now sketch it. So the equal impose canonical commutation relations. So the commutator, equal time commutator of the conjugate fields. See, I have taken same x0 are given by Dirac's prescription. So this is a three-dimensional delta. It nothing but the usual product of usual 1D Dirac delta. Okay, and there are other relations as well. So okay, so imposing them, you will be you have to invert these relations AK in terms of phi and pi, also AK dagger in terms of phi and pi, and when you compute the commutator between A and A dagger, you will eventually lead to integrals over commutator between phi phi, phi pi, and pi pi, but only phi and pi, that commutator is non-vanishing, and you can invert them to these relations. Yeah, so this is a I mean, whatever steps I am jumping, it's a set of work. So I am writing it at exercise, but it would also be okay if you just open a book and understand the steps, but it would be instructive that like you at least do it once. Okay, so for doing this, I should mention that one useful relation, one relation will be very useful. That is you will be, because you will be doing the x integral and leave everything as a k integral, like I have done in the last step. So x integrals will be carried out. So you'll have this. And this is basically a representation. Yeah, here the 2 pi cube appears. So for each dimension, it is just 2 pi. So this is a representation of delta function. Basically, for each dimension, I am stating this because maybe you are familiar with this, is k prime, and to see this, you need to do some, not necessarily, but there is a way to do it by some contour integration. And if you do this, I am not setting L to be, say L is finite, although we'll take L to be infinity, the limit, this is nothing but 2 sine k minus k prime L divided by k minus k prime. If you know that this is in the limit L tends to infinity, this is a representation of delta function. But to satisfy yourself that this is really a delta function, you can multiply with by any function of fk delta k minus k prime and integrate over, say, dk. What you should get? You should get f of okay, k minus k prime f of k. You should finally get, that's the property of the delta function, that you should get f of k, and you can satisfy by further integrating it, that I mean, you can just satisfy yourself maybe by integrating this, that this is pi, which is actually L independent. It does not matter which L you use, it is always pi. So you can see that if you multiply something by f of k and then do the k integral, only if you, okay, what is the another property of delta function? That is nothing but dk delta k minus k prime is 1. So at least you get the 2 pi, and there is a pi, but there is a 2, so you get the 2 pi. So it's proportional to 2 pi times delta. So, but there are systematic ways to see this. I will not be discussing. I will be rather using this relation, and therefore we can find the commutation relations between A and A dagger, and it will be very helpful. Okay, so I should take some questions, and or I can proceed for 5 minutes more, and then I can take all the questions. Maybe that would be better.
Yeah, that sounds good.
Okay, great. So I'll now discuss the Hamiltonian. So that's a problem. So what I did in the Hamiltonian, I found it has a term like A dagger A, and also it has a term A dagger. But A dagger can be written as, and there is a half overall. So this can be written as A dagger using the commutation relation can be written as A dagger A plus the delta. And it is same K, you are integrating over the same K. So it is actually delta 3 of 0. So you can look at the commutation relation here. So usually there is K and K prime. It is delta 3K minus K prime. But in the Hamiltonian, it is the same K what is appearing, and you will get a delta 3 of 0. But keeping in mind, the first term, like when you, why I am doing that, because if you arrange the second term in this way, then it will contribute to the first, like in the expansion, the first term will contribute to the first term in the Hamiltonian, and it will add up. So half plus half is 1. Okay, so this is the first term, and you will get a divergent piece, because delta 3 0, this is the delta which is coming from momentum, and you can think of as the representation I just discussed, that delta is nothing but exponentials, integrals over the exponentials. So there will be the appropriate factors, and K minus K. You can actually set K equals to K minus. Therefore, the in the exponential, the power is 0. So it is exponential of 0, which is equals to 1, and this gives you the volume of the space-time, which is actually a divergent quantity. Okay, so maybe we have infinitely many degrees of freedom, and we are integrating over the total spatial volume. Maybe something is finite, that's the density, but we'll see it is also not. For that, I will first define a vacuum. It is such that it is annihilated by all the AK operator for any K. Immediately, you can see that H acting on the vacuum, the first term will not contribute because AK will annihilate the vacuum. The second term will contribute, and that is looks like the vacuum energy, which will eventually set it to 0, although it is an infinity. Yeah, so maybe we can compute the vacuum energy density. It is this, but you can immediately see that it is still omega k, and for large k, I am not bothering about the factors here. It would be 4 pi k square dk, k square plus m square, which goes to infinity. So that's the first ever divergence you encounter with in quantum field theory, and we need to come up with some remedy. We'll say that we are interested in the difference of eigen energy values, and we'll remove the infinite constant. So it is a constant because it does not depend, it's after integrations over k, it is a constant, although it's this constant is infinity. So this infinite constant will take out by hand, and we'll define a new Hamiltonian and call it the Hamiltonian for the quantum system we want to describe. And you can check these relations. By the way, these relations I am writing holds for both the Hamiltonian, like the full one or the modified one. From this, you judge what is a creation operators and what is an annihilation operators. And I should say that many often you need to have use this commutation relation, like properties of the commutator. Yeah. So you can check this, yes. So it should equally work for both. Yes, so let me just see one thing. Yeah, shall I discuss this today? Yeah, maybe let me tell you about the excited states, and then we will stop. So the vacuum, you know, now H of vacuum is 0. Excited, these are the momentum states. Which is defined as some bunch of creation operator acting on these. And you can check that n hat, this should be the number operator that basically counts the number of particles in your state, and it is indeed an eigenstate of the Hamiltonian with the energy. So this is a particle state where they are free particles. So it is nothing but the energy of n free particles with momenta p1 up to pn. And since a dagger commute, you can see it here that only a dagger is not commuting, but a and a dagger at different momenta even they commute. Therefore, whenever there is a bunch of creation operators that acts on 0, you can arrangement does not matter. So this state, since this implies the state has a symmetry under interchange of the label this. So a single mode can be populated. For example, you can act this n times acting on 0. You will get nothing but n times omega p as the energy. So H of this will be this time again the state. So even a single state can be like excited, and so a same energy can be populated by n particles. So that is the Bose symmetry, and that should be I think an good place to stop for today, and I can take all the questions.
Okay, there are some questions. In the chat, the question was, okay, let me stop the recording.